Here you can see Sake, it's one of our other monkeys, typing on a keyboard. But now this is telepathic typing. So to be clear, this is he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, can't actually spell, and so I don't want to oversell this thing. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. I think it's also important to show that Sake actually likes doing the demo, and is not like strapped to the chair or anything. So So the monkeys actually enjoy doing the demos because they get the banana smoothie, and it's kind of a fun game. So I guess what I'm trying to make is like we care a great deal about animal welfare, and I'm pretty sure like our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for the first two applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision.
We can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field. It's about a surface area equal to a credit card on each side. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right.
So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. For implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of a few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. So here it is. That's our R1 robot with our patient Alpha, who's lying comfortably on the patient bed. This is what we call the targeting view. So what you're seeing is this is a picture of our brain proxy. And the pink represents the cortical surface that we want to insert our electrodes into, and the black represents the vasculatures that we want to avoid. So this is another view, real quick. On the left is the view of the insertion area, and on the right, what the robot's going to do is it's going to peel the array, the threads, one by one from its silicon backing, and insert it into the targets that we predetermined in the targeting view. So there you go. That's the first insertion. So we're going to see a couple more insertions. The whole process of inserting about 64 threads in our first product is going to be around 15 minutes for this robot.
Since I joined in 2017, we've also done a handful of iterations to optimize the thread insertions of the robot. One of the challenges that we've had to face has to do with the optomechanical packaging. So as you can see here, there's about 3 primary optical paths that are really valuable for us to have reliable thread insertions. One is the visible imaging of the needle inserting the thread. And then another is the laser interferometry system called OCT, optical coherence tomography, that gives us the precise position of the brain while it's moving in real time. And then also we have to provide lighting and illumination to see what's going on in the visible light camera. And doing all this where the needle is at the bottom of the craniectomy, especially when it's close to the skull wall, can be pretty difficult to fit everything and be able to see it. So the way that the team solved this is by putting all 3 of these optical paths into one optical stack using photon magic or polarization, whatever you want to call it. And that enables us to do vessel avoidance in real time. So as I mentioned, the brain is moving, and where we place targets in the beginning may not be where you want to insert at the moment the needle is going down there. So the robot can actually detect the vessels and then determine if we're going to insert onto a vessel or not, if it's safe to insert. And then that way we can avoid inserting onto major vessels.
So for persons with spinal cord injury, the connection between the brain and the body is severed. The brain continues functioning normally, but it's unable to communicate with the outside world. You've already heard about how we can use the N1 link as a communication prosthesis to help someone with spinal cord injury control a computer or a phone, but it can also be used to reanimate the body. Let me show you how. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Okay, so here's a pig walking on a treadmill, and you may have seen something like this before in a previous Neuralink presentation. But unlike before, this pig has more than one Neuralink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. Okay, so let's stimulate on an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting, but if you look carefully, you can see how the leg is moving. We can stimulate on a great variety of threads and produce different movements and actually sequence them spatial temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. We have a lot of work to do to achieve this full vision, but I hope you can see how the pieces are all there to achieve this. And if you find this prospect as exciting to you as it is to me, I hope you'll consider joining us here at Neuralink. Thank you.